Imagine a gigantic machine that bends a thick metal sheet with incredible precision, like it's just a piece of paper. It operates with such force and finesse that every millimeter of the bend is a result of engineering perfection. This is a press brake, indispensable in manufacturing car bodies, home appliances, aircraft, and even military equipment. How does this machine work? What forces are involved in bending metal? And why can't modern factories imagine production without it? Let's figure it out. Press brakes operate with forces ranging from 40,000 to over 4 million pounds force, depending on the type of equipment and the thickness of the metal. For example, bending a steel sheet 0.4 inches thick and 10 feet long requires a press brake with at least 350,000 pounds force. The most common models have a working length of 4 to 20 feet, and positioning accuracy can reach 4/10,000ths of an inch, thanks to computer numerical control. The punch's descent speed is typically around 4 inches per second, but during the bending phase, it slows down to 0.4 or 0.6 inches per second for precise angle control. Companies like Ford, General Motors, and Tesla use press brakes to form body panels, frames, and chassis components. For instance, bending the aluminum body sheets for the Tesla Model Y utilizes servo-hydraulic press brakes with a working area length exceeding 12 feet. Just look at the manufacturing of a true giant. This is a press brake 52 feet long. That's like the length of a double-decker bus. To make such a machine, many large metal parts are welded together. Welding is like gluing metal, but very strong and reliable. After welding, all joints are checked with special instruments to ensure the machine will be sturdy and safe. Then, the parts are ground and fitted so that everything works perfectly. The giant parts of the press brake weigh hundreds of tons. That's like 2 large airplanes. To lift and place them, special cranes and hydraulic lifts are used. Machines capable of lifting extremely heavy objects. After all the parts are assembled, hydraulic systems are connected to the press brake. These are like the machine's muscles, giving it the power to bend metal. Press bending is used in the aerospace industry to manufacture stiffeners, frames, and fuselage skin. High precision is particularly crucial here, as an error of even 0.002 of an inch can be critical for an aircraft's aerodynamics. So, how does this giant press brake work? When a metal sheet is placed on the press brake's special table, or bed, the machine applies immense force from above. It's like when you press down on modeling clay to shape it. The upper part of the press, called the punch, and the lower part, the die, work together to bend the metal exactly as needed. Modern press brakes have a computer that helps precisely adjust the force, bend angle, and speed. This allows for making identical parts with perfect dimensions again and again. For forming armored panels in the production of armored vehicles, particularly at Oshkosh Defense, a manufacturer of military vehicles, hydraulic presses exerting 2 million pounds force are used. They are capable of working with thick steel plates over 1 inch thick. Shipbuilding is one of the most complex industries, where metal parts have unique shapes and large dimensions. Special presses are used for their manufacture, capable not only of bending metal, but also stretching, twisting, and forming it into complex structures. Such presses are enormous machines, sometimes several stories tall and long. They have powerful hydraulic systems that generate immense pressure, hundreds or even thousands of tons. Thanks to this, metal can be forced into the desired shape, even if it's very thick and strong. Metal sheets or panels are bent at a specific angle to give them the required geometry. This could be a bend for the ship's side or a stiffening rib. Using the press, the metal is stretched, making it thinner and more elastic in certain areas. This is important for creating smooth curves and streamlined hull shapes. Some parts require twisting to achieve a spiral or other complex form. The press allows this, controlling the force and direction of the load. Large presses are equipped with automatic control systems that monitor pressure force, movement speed, and forming accuracy. This ensures that each part meets technical requirements and will be reliable in use. A ship's hull must be strong, watertight, and resistant to the impact of waves and storms. Therefore, parts manufactured on such presses must be perfect in shape and quality. Errors could lead to damage or accidents at sea. Where there are giant presses, there are always guillotines nearby. A guillotine shear is a powerful machine that cuts metal like scissors cut paper. It is very precise and can work with thick metal sheets, preparing them for further processing. A guillotine shear has two main parts, a stationary lower blade and a movable upper blade. When the operator starts the machine, the upper blade quickly descends and cuts the metal sheet pressed against the lower blade. Thanks to precise adjustment of the gap between the blades, the cut is clean and straight, without burrs or deformation. Guillotine shears come in various sizes and capacities. Some can cut metal several inches thick, which is hard to imagine compared to the thickness of a regular sheet of paper. For this, the machine has very strong and sharp blades, as well as a powerful drive, either electric or hydraulic. Modern guillotine shears are equipped with computer numerical control, allowing precise parameters for the cut to be set: length, angle, speed. This is very important when many identical parts need to be made. The machine performs the work quickly and without errors. For operator safety, guillotine shears are equipped with special protective guards, motion sensors, and emergency stop buttons. This prevents injuries and ensures safe operation even under heavy loads. Guillotine shears and large press brakes are an integral part of modern metal structure manufacturing. They allow for making parts quickly and accurately, using metal with maximum efficiency, minimizing waste, creating complex shapes impossible to make by hand, and improving the quality and reliability of products. In ventilation and air conditioning systems, bending metal ducts from thin sheet steel or aluminum is a daily task. Here, fast press brakes with automated feeding are used, allowing for the production of 500 parts per shift. Furniture manufacturing and home appliances. Companies like Whirlpool or Steelcase use press brakes to create housings for refrigerators, washing machines, cabinets, and so forth. Here, not only the force, but also the aesthetic precision of the bend is important. The largest hydraulic press in the world has a force of 150 million pounds force. It was created to form parts for rockets, airplanes, and nuclear reactors. The structure's height is over 90 feet, and almost half of the machine is hidden underground. In the United States, in Cleveland, Ohio, operates the famous 50,000-ton press. This is a Wyman Gordon project, built in the 1950s during the Cold War. It is still used today to manufacture parts for military aircraft, such as landing gear and spars for the F-15 and B-52. For the production of wing sections for the Airbus A380, press brakes over 65 feet long are required. They work with aluminum-magnesium alloys, which are difficult to process without special preheating of the material. Komatsu and Amada factories have press lines where robots feed, position, and remove parts without human intervention. One such press can make up to 150 bends per hour. As for the guillotine, its invention is mistakenly attributed to Dr. Joseph Guillotine, who only proposed its use. According to historical data, the guillotine was initially used precisely as an instrument for carrying out the death penalty. It was introduced in France in 1792 as the sole tool for execution, regardless of the condemned person's social status. The guillotine as a functioning device existed in Germany, Great Britain, and Italy, even before the year 1300. Now, the guillotine shear for cutting metal is one of the most sought-after pieces of equipment in almost all manufacturing industries. Who would have thought that such a gruesome device, 700 years later, would be perceived as something that improves life rather than ending it? Imagine this: red-hot metal, up to 33 feet long, being pushed with a dull roar into a massive rolling mill. No seams, no joints, just a perfectly smooth steel pipe appearing literally out of nowhere. These aren't scenes from a science fiction movie, but the daily work at one of the most unique factories in the world. How is it possible to create a pipe without a single seam? One that withstands pressure of hundreds of atmospheres and operates where other materials simply melt. Ready to walk through the scorching workshop and find out how true engineering perfection is born? Then let's embark on a journey to an amazing steel pipe factory. It all starts with cylindrical billets. Each one weighs 1 ton. That's like 3 smart cars in a metallic body. They are transported by rail or truck because other transport simply can't handle such a load. Each billet is secured on special pallets or in retaining clamps so it doesn't shift during movement. Upon arrival at the factory grounds, unloading is automated using cranes, manipulators, or hydraulic carts. The billets immediately go to the receiving area, where they are checked for compliance with technical specifications, chemical composition, shape, integrity. Before the hot steel becomes a pipe, it undergoes a truly dramatic inspection. Defects shall not pass. First, the billets get an X-ray. Well, not exactly X-ray, but something similar for metal. Ultrasonic testing. You heard that right. The billet is coated with a conductive gel, like for a human ultrasound, and a transducer is moved across it. Special transducer ears shoot sound waves at a frequency of 5 MHz. That's 100 times higher than submarine sonar. This is how they search for cracks and inclusions of foreign materials within the billets. The system builds a 3D map of defects with an accuracy of 1/100th of an inch. If it finds a saboteur, the billet is marked with red paint and sent to metal hell for remelting. Next comes the chemical analysis. For this, 5 or 10 metal samples are taken from each batch and sent to the factory laboratory. There, they use special spectrometers, devices that read the metal's composition using light emissions. The spectrometer determines over 12 elements in the composition in seconds. During the analysis, the sample is treated with an electric spark or a laser. This excites the atoms on the metal surface, causing them to emit light of different wavelengths. Each chemical element glows uniquely, so the device recognizes exactly which elements are present in the steel and in what quantities. How much carbon, manganese, chromium, nickel, or phosphorus. This analysis takes only a few minutes, but provides a complete picture of how well the billet meets technical requirements. If the composition isn't perfect, the batch might be rejected or redirected to other production lines. From 1 to 3% of billets are sent for remelting. Defective billets are sent to an electric furnace with a temperature of 2,900 degrees Fahrenheit, where the steel becomes liquid again. All the post-melting slag is used for road construction. 90% of defects are detected during the ultrasonic diagnostic stage. It's like finding a needle in a haystack in 10 seconds. The chemical analysis takes 17 seconds, faster than you order coffee at Starbucks. Quality control costs range from $50 to $100 per ton of steel. But it's better to overpay than to later have a well blowout due to low quality material. Quality control is the Karen's filter for steel. Only 97 to 99% of billets become pipes. The rest are sent for reincarnation. So, when you hold coffee in a steel thermos, know this: its ancestors went through real metal special forces training. After checking the chemical composition, the cylindrical steel billets are delivered to the heating section, the place where a giant furnace stands. These furnaces are true giants, capable of holding over 1,000 billets simultaneously. To load the billets inside, massive automated cranes or special manipulators with heat shields are used. The billet is picked up using gripping mechanisms, large metal fingers or tongs that securely hold the heavy part. The crane carefully moves the billet to the open loading door of the furnace. At this time, the temperature inside can exceed 2,400 degrees Fahrenheit, so the entire process is maximally mechanized. People operate the machinery remotely from a safe cabin or control panel. The furnace has special guides or pushers that help place the billets carefully inside, so that heat distributes evenly. After loading, the furnace doors are hermetically sealed, and gradual heating to the working temperature begins. In 2 hours, the steel transforms into a plastic mass. The billet becomes ready for forming, like melted chocolate. Next, the monster drill comes into play. It weighs 12 tons. That's like 2 elephants. The red-hot steel billets, massive cylinders, are removed from the furnace and delivered to a special rolling machine, where one of the most crucial stages of seamless pipe production begins, creating the hole inside. The piercing process looks impressive. The red-hot billet is placed on a special support ring in front of the piercing mill, where a thick, cone-shaped rod awaits it, the so-called piercer point or piercing mandrel. At this moment, immense force is at work. The billet is rotated between two conical rolls, spinning in opposite directions. The rolls don't just squeeze the billet, they create strong rotational and axial pressure, causing the billet to stretch along its axis, flowing around the piercer point. To avoid cracks or ruptures, the pressure and temperature during piercing are controlled very carefully. If the billet cools too quickly, or the pressure is distributed unevenly, it can break or lose the required shape. Therefore, the process runs without interruption, and with strict adherence to all parameters. This process is called the Mannesmann method, named after the German engineers who invented it in 1885. After the initial piercing, the resulting rough pipe is called a hollow shell or bloom. The wool thickness of the shell is approximately 2 inches. It still has uneven walls and may contain small defects, so the next stage is rolling and calibration, where the pipe is stretched, straightened, and brought to the required dimensions and wool thickness. The red hot steel billet enters under giant rolls 5 feet in diameter. Under tremendous pressure, it's drawn out into a slender pipe up to 40 feet long, faster than you can blink. This is where the major league of precision reigns. Wall thickness is reduced from 0.8 inches to 1.2 inches, with a deviation of less than 4/1000ths of an inch. That's thinner than a human hair. And all this happens at staggering speeds of 16 to 49 feet per second, faster than Usain Bolt on his best day. It's like rolling out the thinnest pizza dough. Only instead of dough, it's a red hot steel core. And instead of a kitchen board, there's a shower of sparks and the roar of the rolls. Next, fire gives way to ice. Well, not ice, but cooling. The workshop heat is 122 degrees Fahrenheit, so workers wear special suits as if preparing to conquer Mars. Meanwhile, the pipes gradually cool in the open air. Their temperature slowly drops to 570 degrees Fahrenheit to avoid deformation and cracking. When the pipe emerges from the fiery dance of rolling, it resembles an enraged dragon, powerful, but bent into wild spirals. That's when the 8-roll giant enters the scene, a mechanical Hephaestus that will forge perfect forms. Its rolls, stronger than the rocks of Olympus, bend the steel with a force of 500 tons. That's like putting 250 Land Rovers on the pipe. But this force isn't a destroyer, but a surgeon. It corrects curvatures smaller than the thickness of a hair. And then comes the time for lasers. They scan every millimeter, finding the smallest defects, invisible cracks, minor unevenness. And when they find something, plasma scalpels enter the game. 10 times hotter than lava, they cut the metal like cosmic lightning bolts. All that remains of the defects is smoke and legend. If the Colossus of Rhodes were made of such pipes, it would still be standing today. Imagine taking the air you are breathing right now and turning it into a substance that can freeze ice cream in 3 seconds and make a banana tough enough to hammer nails. This is not magic. It is liquid nitrogen. Every second, it is used in medicine, science, the food industry, and in some top-secret experiments. Temperature, minus 321 degrees Fahrenheit. 1 sip, and you lose part of your stomach. 1 breath, and you unlock tomorrow's technology. How does the coldest substance on Earth get made from regular air? How is it transported, stored, and used? And why can it save or destroy? Watch closely and prepare to be amazed. It all begins with air. Yes, the very same atmospheric air that surrounds us. This happens inside industrial air separation units. These systems come in all sizes, from massive factory installations to mobile units for medical use. Air is sucked in using compressors. Then it passes through filters. First, coarse filters that remove dust, insects, and pollen. Next, fine filters get rid of moisture, carbon dioxide, and other impurities. Once cleaned, the air is compressed using powerful machines, increasing both pressure and temperature. Then, it is gradually cooled in heat exchangers. When the high-pressure cooled air moves through a narrow nozzle into a low-pressure chamber, it expands rapidly. That sudden expansion causes a major drop in temperature. This is the key moment. The gas becomes cold enough to start condensing into a liquid. This process repeats several times. Each cycle drops the temperature further. Eventually, nitrogen reaches its liquefaction point. This technique does not work with every gas, but it is perfect for nitrogen. Thanks to this, we can create liquid nitrogen from ordinary air. Once the air is chilled and liquefied, it goes through fractional distillation. This process separates the liquid mixture into components based on their boiling points. Inside a special distillation column, the liquid air is gently reheated. Nitrogen has the lowest boiling point, around -320 degrees, so it evaporates first and rises to the top. Oxygen boils at -297 degrees, so it evaporates later and does not climb as high. Argon, with a boiling point around -302, settles somewhere in between. The column forms a thermal gradient, colder at the top, warmer at the bottom. The gases evaporate and condense over and over, becoming purer with each cycle. It all works without additives, automatically, and with minimal losses, thanks to precisely managed pressure and temperature. Since nitrogen makes up roughly 78% of air, extracting it takes powerful equipment, a complex network of pipelines, and exact temperature control. Once separated, liquid nitrogen is stored in special vessels, cryostats, or Dewar flasks, which look like futuristic thermoses. These vessels keep temperatures low and prevent evaporation. They are not just metal barrels. They have double walls with a vacuum in between to block heat. Some also include reflective coatings to minimize radiant heat loss. These containers can preserve liquid nitrogen for several days to several weeks, depending on volume, insulation, and how often they are opened. Often, nitrogen is used right on site. For example, medical facilities use liquid nitrogen for cryopreservation of cells, embryos, vaccines, and tissues. In the food industry, it is used for flash freezing. Contact with liquid nitrogen instantly freezes food, locking in texture, taste, and shape. But when it needs to be transported, preventing evaporation is critical. That is because nitrogen quickly turns back into a gas. Portable dewars, cryotanks, and cryotank trucks are used. Small dewars are handy for labs and clinics. Cryotanks are massive, like giant gas tankers, and are hauled by trucks with special mountings and ventilation. Cryotank trucks are purpose-built vehicles with insulation and pressure regulation to avoid explosions from expanding gas. Sometimes, liquid nitrogen is produced directly on site, at large research centers or hospitals, to avoid reliance on deliveries. How did humanity tame one of the coldest, most inert substances on Earth? It all began with nitrogen. Discovered in the year 1772 by Scottish chemist Daniel Rutherford, who was studying air and found a gas that could not sustain fire or life. That was nitrogen, colorless, odorless, inert. But liquefying it required cold and pressure, and humanity needed more than 100 years to figure that out. The first liquid nitrogen was produced in 1883 by Polish scientists Zygmunt Wroblewski and Karol Olszewski. They built a system that cooled air so much that nitrogen, its main component, turned into a liquid. That was a breakthrough. In the 20th century, cooling tech advanced fast. Scientists improved gas liquefaction methods and eventually developed the Joule-Thomson cycle, which relies on pressure drops to efficiently liquefy gases. In the 1930s and 50s, liquid nitrogen made its way into industry and medicine, starting in labs, then into surgeries, biobanking, and physics experiments needing ultra-low temperatures. Today, liquid nitrogen production is a global-scale operation. It is made in massive air separation plants around the world. What was once just background gas, making up almost 80% of air, has become a superstar of industrial science. Some chefs even make ice cream live, pouring cream into a bowl, adding liquid nitrogen, mixing, and voila, instant dessert. The cold is so intense, It freezes the treat in seconds. Dip a banana in liquid nitrogen for a few seconds, and you can hammer nails with it. Seriously. Want to try? Inhaling cold nitrogen vapor can temporarily change your voice, like helium, but deeper. But do not try this. It is dangerous without protection and special equipment. Some people have dipped old socks into dewars of liquid nitrogen. Result? The fabric becomes brittle like glass and crumbles in your hands. A perfect way to destroy evidence. If you are a sock. Pour liquid nitrogen on a warm floor, and it turns into a dramatic cloud. It vaporizes instantly, making you feel like you are stepping through a Hollywood portal. What should you never do with liquid nitrogen? Even if it looks cool, never stick your hand into it. Online videos show people dipping fingers and pulling them out unharmed. That is the Leidenfrost effect. A brief protective vapor layer forms around the skin, but if you hesitate for a second too long, hello frostbite, do not try it. Seriously. Never drink it. Yes, that happened too. In several restaurants, smoky desserts were served with a drop of liquid nitrogen. One careless guest sipped before it had fully evaporated and lost part of their stomach, literally. Afterward, several countries banned such stunts. Do not pour it on your bathroom floor. The vapor looks cool, sure, but tiles can crack from thermal shock. Plus, the risk of suffocation in a small space is real. Nitrogen displaces oxygen. Do not pour it in the toilet. Not because it will definitely break, but it might. And because pipes can burst. Some TikTokers have proudly frozen their plumbing. Utility crews must love them. If you are not an engineer or a molecular gastronomy chef, do not try freezing food or fruit from the inside. Liquid nitrogen can rupture the skin and explode in your hands, especially with high moisture items. So yes, liquid nitrogen is amazing, but it is also incredibly dangerous. Respect the frost. Every year, people throw out 4.4 billion pounds of washing machines. That is like 200 Eiffel Towers made of metal and plastic. But what if your old washer could snag you $200 from Samsung or LG, and then come back to life in a totally new way? In this video, we are going to show you how shredders rip steel apart in seconds, magnets snatch out copper, and plastic gets transformed into new gadgets. Why are brands willing to pay for your old junk? And how can a single machine either help save the planet or end up poisoning it? The first 30 seconds will spill a secret that is going to change the way you think about trash forever. You do not want to miss it. Lots of big brands and electronic stores have programs where you can trade in your old stuff, or they will haul away your old appliance for free when you purchase a new one. For instance, in the United States, companies like Whirlpool, LG, and Samsung have programs like this. Over in Europe, they have initiatives under the Waste Electrical and Electronic Equipment Directive. The details can be different depending on the company. Some will just haul away your old appliance, while others might give you a discount toward your new purchase. Whirlpool in the United States, for example, might offer anywhere from $50 to $100 off a new appliance if you're trading in an old washing machine. LG and Samsung sometimes run special promotions where they might offer $100 or even $200 back. Over in Europe, some programs might let you get up to a 10% discount on a new appliance. But more often than not, the discounts are not that big. Most companies really look at this as more of an environmental effort, not just a strategy to pull in customers. In a lot of cities, you will find electronic waste collection centers where people can drop off their old washing machines themselves. These centers often team up with local city governments or private recycling companies. In some countries, like Germany, the United Kingdom, and the United States, there are city-run services that will actually come and pick up bulky electronic appliances. For example, in New York City, you can schedule a free pickup through the city's own program called NYC Safe Disposal. There are also some companies that focus specifically on recycling metals. They might actually buy your old washing machine from you, or at least take it off your hands for free. These companies then send the appliances off to be taken apart, where they pull out all the valuable stuff like metal, electronics, and plastic. First things first, the machines get sorted into different groups. Ones that still work, ones that kind of work, and ones that are completely broken. The machines that still work might get fixed up and resold, but the ones that are too far gone head off to be taken apart. The teardown process starts by taking off the outside panels, the door, and the drum. Things like motors, electronic components, wiring, and pumps are separated out because they can often be reused as parts or melted down for their materials. The different types of metal get sorted separately, like stainless steel, aluminum, and copper. Plastic parts are also gathered up and sent off for recycling. This whole process can be done by hand, or it can happen on special automated lines where machines shred the main body and then use things like magnets and air separators to sort out the different materials. These automated recycling lines for washing machines usually involve several steps, and each step is designed to separate out specific types of materials. First, the washing machines are loaded onto a conveyor belt that feeds them into powerful rotating shredders. The blades on these shredders are strong enough to rip through the metal and plastic bodies, breaking them down into pieces roughly 1 to 4 inches across. Once everything is shredded up, the mix of materials moves past magnetic separators. These magnets grab onto any metals that are attracted to magnets, like steel and cast iron, pulling them away from all the other stuff. Next up is something called an eddy current separator. It uses a different kind of magnetic field to actually push away the non-ferrous metals, things like aluminum and copper. Plastics and other lightweight materials get separated out using air separators. Basically, strong blasts of air blow the lighter bits, like plastic flakes, upwards and into collection bins, while the heavier stuff stays put on the conveyor belt. Toward the end of the sorting line, whatever materials are left might go through optical scanners. These scanners can analyze what the pieces are made of and sort them even further, sending them to the right place for more processing or final disposal. So, after all this sorting with air separators and optical scanners, the different materials head off to their own separate processing lines. This is where the plastic, metal, glass, and anything else gets processed so it can be reused or recycled properly. The leftover metal pieces, like the steel parts, are shipped off to metal processing plants. There, they get melted down and eventually used to make brand new products. Remember those magnetic separators? They are super effective at pulling out iron and steel, which then get sent off to be melted down. The plastic parts get shredded into smaller pieces and then usually compressed into dense bales or blocks. These bales can then be shipped to specialized factories where they will be used to make new plastic items, or they might become part of the raw material mix for new appliances or other tech gadgets. If the washing machine had any glass parts, maybe in the door window, that glass gets cleaned really well to remove any gunk, and then it can be melted down to make new glass products. Any leftover materials that cannot really be recycled, maybe certain kinds of rubber or complex mixtures of stuff, usually end up getting sent for final disposal, often meaning they go to specially designed landfills. These kinds of sorting and recycling setups drastically cut down on the amount of waste that just gets dumped in landfills. Plus, they help get valuable raw materials back into the economy so they can be used again. Sometimes, especially for really tricky materials, they have to use more advanced techniques, like thermal decomposition, which uses heat or special chemical treatments. These methods come into play for stuff that is hard to separate just by shredding and sorting mechanically, or for materials that need extra processing to make sure they do not cause pollution or release harmful substances. Good examples are certain plastic components that have other materials embedded in them, like plastic with metal pieces fused inside or attached rubber seals. Materials like these often cannot be sorted easily using the standard methods, so they need special treatment to break them down and separate the different parts. Rubber parts, particularly those made with complex chemical additives, are often tough to recycle effectively because of their complicated structure. For materials like that, processes like thermal decomposition or other chemical methods might be used. The goal is to basically unzip them into simpler building blocks that can potentially be reused or at least disposed of more safely. In situations where the appliance contains hazardous stuff, think mercury in old switches, or maybe some types of batteries or old lighting components, those materials absolutely have to be handled with special procedures. This might involve a chemical process designed to neutralize the dangerous parts, or maybe one that locks them up safely so they can be disposed of without causing harm. Materials like polyurethane or polyester, which you often find used as insulation around wires or in various other parts inside appliances, might also be treated with thermal decomposition. This helps break them down into simpler substances that could potentially be recycled. And then you have situations where washing machines or other electronics contain complex composite materials. Stuff made of several layers of different materials bonded together, like plastic fused with metal layers or reinforced with fibers. These often require very specialized processing to carefully separate the layers so that each material can hopefully be recycled on its own. Overall, the reason for using all these different technologies is to make the whole disposal process as efficient as possible and to minimize the harm done to the environment. Because if these materials are not handled the right way, you could end up with pollution or dangerous chemicals leaking out into the ground or water.